Picture this. In a small, dimly lit office in 1915, a man sits at his desk, his wild hair illuminated by flickering lamplight. His fingers, stained with chalk dust, dance across papers filled with mysterious equations. This man is about to shatter our understanding of the universe itself. Albert Einstein, not yet the cultural icon we know today, is on the verge of completing what many consider the most beautiful theory ever created. What if I told you that everything you think you know about gravity is wrong? That the apple didn't fall on Newton's head because of some mysterious force, but because space itself is bent and curved? That time isn't the steady tick-tock we experience, but a fluid dimension that can stretch and compress like rubber? Einstein's general theory of relativity didn't just change physics, it transformed our entire conception of reality. It revealed a universe more bizarre and magnificent than anyone had imagined, where black holes tear through the fabric of space-time, where the past and future are relative concepts, and where the very cosmos breathes and expands like a living thing. Today, we're embarking on a journey that will challenge everything you think you know about space, time, and gravity. We'll explore a theory so profound that even a century later, it continues to reveal new secrets about our universe. A theory that powers your GPS, explains the birth of galaxies, and predicted the existence of black holes decades before we could see them. But before we dive into the mathematical beauty of general relativity, I want you to forget everything you learned in physics class. Because the universe Einstein discovered is stranger and more beautiful than anything in our textbooks. Are you ready to have your mind bent by the true nature of reality? If you're fascinated by the mysteries of our universe and want to join me on more mind-bending journeys through space and time, make sure to hit that subscribe button and join our community here at Exploring the Universe. Tap the like button if you're ready to have your understanding of reality transformed forever. And remember, in a curved universe, every like creates a ripple in space-time that brings us all closer together. Let's begin our journey into Einstein's universe. Imagine holding a bed sheet taut in the air. Now place a heavy bowling ball in the center. See how the fabric dips and curves? This simple demonstration captures the essence of what might be the most elegant scientific theory ever devised: general relativity. But what exactly is general relativity? At its heart, it's Einstein's masterpiece that completely reimagined gravity. Newton told us that gravity was a mysterious force of attraction between objects. Einstein showed us something far more profound. Gravity isn't a force at all. Instead, general relativity tells us that what we experience as gravity is actually the curvature of something called spacetime. Think of spacetime as a four-dimensional fabric that makes up the universe itself. 3 dimensions of space, up, down, left, right, forward, backward, woven together with time into a single cosmic tapestry. Here's where it gets fascinating. Every object with mass or energy warps this cosmic fabric. The sun creates a deep well in spacetime, and the Earth rolls around this curve like a marble circling a funnel. Our planet isn't being pulled by some mysterious force. It's simply following the natural contours of curved spacetime. But Einstein's theory goes even further. It tells us that space and time aren't fixed and absolute as Newton thought. They're dynamic, flexible, and intimately connected. Time moves slower near massive objects. Space can stretch and bend. The geometry of the universe itself changes depending on the matter and energy within it. This isn't just abstract mathematics. General relativity makes precise predictions that we've confirmed time and time again. It predicted the existence of black holes, where space-time curves so severely that even light can't escape. It predicted gravitational waves, ripples in space-time that we finally detected in 2015, a century after Einstein proposed their existence. Perhaps most remarkably, general relativity revealed that our universe isn't static. It's expanding, growing larger with each passing moment. This prediction led directly to our modern understanding of the Big Bang and the evolution of the cosmos itself. Let's dive into one of the most mind-bending concepts in physics, space-time. But before we get lost in the mathematics, I want you to do something simple. Think about how you would tell someone where to meet you. You'd give them 3 pieces of information: the street address and the time. Without realizing it, you've just described a point in space-time. You see, everything that happens in our universe requires 4 coordinates to be fully described. 3 for space, like longitude, latitude, and height, and 1 for time. Einstein's revolutionary insight was realizing that these aren't separate things. Space and time are fundamentally interwoven, like threads in a cosmic tapestry. Think about it this way. When you look at the stars in the night sky, you're not just looking through space, you're looking back in time. The light from Andromeda Galaxy takes 2.5 million years to reach us. When you observe it, you're seeing where it was 2.5 million years ago. This is spacetime in action. You cannot separate the where from the when. Spacetime isn't just some abstract concept. It's the stage upon which the entire cosmic drama unfolds. Every event that has ever happened or will happen, from the Big Bang to you reading this script, is a point in spacetime. Scientists call these points events, and they're as real as the device you're watching this video on. But here's where it gets truly fascinating. Spacetime isn't rigid or fixed. It can bend, stretch, and warp. If you're traveling very fast, or if you're near a very massive object, your experience of time literally changes. This isn't science fiction, it's happening right now. The GPS in your phone has to account for the fact that time moves slightly differently for satellites in orbit than it does for us on Earth's surface. Einstein showed us that everything, every particle, planet, and galaxy, exists in this four-dimensional theater we call spacetime. When objects move through space, they trace out what we call world lines through spacetime. Your entire life, from birth to death, is a world line, snaking its way through the cosmic fabric of reality. And just as a stage can affect the performance of a play, spacetime affects everything within it. The way it curves and bends determines how objects move, how light travels, and even how time flows. This is why understanding spacetime is crucial to understanding gravity itself. But that's a story for our next segment. Consider this. Every heartbeat, every breath, every moment of your existence isn't just happening in space, and it isn't just happening in time. It's happening in spacetime. You are quite literally surfing through the fourth dimension right now, whether you realize it or not. Remember that bed sheet demonstration I mentioned earlier? Let's take it further. Imagine that sheet is made of the finest silk, stretching out to infinity in all directions. Now place a bowling ball in the center. The fabric dips and curves, creating a well around the ball. If you were to roll a marble near this well, it would spiral inward toward the bowling ball. This simple demonstration captures one of the most profound ideas in physics, the curvature of spacetime. But reality is even more fascinating. In our universe, every object with mass, from a grain of sand to a supermassive black hole, creates its own dip in the fabric of spacetime. The sun, with its enormous mass, creates a deep gravitational well that extends throughout our solar system. The Earth, being less massive, creates a smaller but still significant curve. Even you, right now, are ever so slightly bending the spacetime around you. This is what gravity really is, not a mysterious force reaching out through empty space, but the very geometry of spacetime itself. When you jump up, you're not fighting against some invisible force pulling you down. You're actually trying to climb up the curved wall of Earth's gravitational well. When you fall, you're simply following the natural contours of curved spacetime. The more massive an object is, the more dramatically it warps the spacetime around it. A neutron star, with the mass of our sun crushed into a sphere the size of a city, creates such severe curvature that light itself bends noticeably around it. And then there are black holes, objects so massive that they puncture spacetime itself, creating a region from which nothing, not even light, can escape. This curvature explains why planets orbit the sun, why galaxies hold together, and why you stay firmly planted on Earth's surface. It's a dance of mass and geometry playing out across the cosmos. The Earth isn't being pulled around the sun by invisible strings. It's following the deepest path through curved spacetime, like a ball rolling around the rim of a funnel. But here's something even more mind-bending. This curvature affects time as well as space. Time actually flows more slowly at the bottom of a gravitational well than at the top. This isn't just theory, we've measured it. Time passes slightly faster at the top of Mount Everest than at sea level. Your head is aging ever so slightly faster than your feet, simply because it's further from Earth's center of mass. The mathematics behind spacetime curvature is complex, but the principle is beautifully simple. Mass tells spacetime how to curve, and curved spacetime tells mass how to move. This single insight explains everything from the orbits of planets to the collision of galaxies, from the bending of starlight to the existence of black holes. Imagine you're rolling a marble along a perfectly flat table. It travels in a straight line, right? Now, what if that table wasn't flat, but subtly curved? The marble would follow the contours of that surface, appearing to curve its path while actually taking the most natural route available. This simple example unlocks one of the most profound secrets of our universe: how objects move through curved spacetime. In Newton's view of the universe, objects moved in straight lines unless a force acted upon them. Einstein showed us something far more elegant. Objects always move in the straightest possible path, but through curved spacetime. These paths are called geodesics, and they represent the natural flow of motion through our warped cosmic fabric. Think about Earth's orbit around the Sun. In the Newtonian world, we needed a mysterious gravitational force to explain why Earth doesn't fly off into space. But in Einstein's universe, Earth is simply following a geodesic, the straightest possible path through spacetime that has been curved by the Sun's massive presence. It's like a race car following the banking of a curved track, no mysterious forces required. This principle applies to everything in the cosmos. When light from a distant star passes near a massive galaxy, it follows a curved path, not because gravity is pulling on it, but because it's following the natural geometry of curved spacetime. This is how we get gravitational lensing, where massive objects can bend and focus light like a cosmic magnifying glass. The dance of galaxies in cosmic clusters, the spiraling of binary stars around each other, even the way your coffee forms a whirlpool when you stir it. All these movements reflect objects following geodesics through curved spacetime. It's a cosmic choreography written in the language of geometry. But here's where it gets even more fascinating. These paths through spacetime aren't just curved in space, they're curved in time as well. An object following a geodesic near a massive body doesn't just move through space differently. It experiences time differently too. This is why GPS satellites need to account for both special and general relativity. They're literally moving through a different geometry of spacetime than we are on Earth's surface. And in the most extreme cases, near black holes, these geodesics can loop and twist in mind-bending ways. Light itself can orbit a black hole in a photon sphere, trapped in a perfect circle by the severe curvature of spacetime. Matter falling into a black hole follows spiral paths that appear to freeze in time from our perspective, while experiencing a very different reality from its own. Even the expansion of the universe itself can be understood through this framework. Galaxies aren't flying away from each other through space. Space itself is expanding, and they're simply following their geodesics through this expanding spacetime. The year was 1919, and humanity was about to witness one of the most dramatic moments in scientific history. Two teams of astronomers, led by Sir Arthur Eddington, embarked on dangerous expeditions to remote parts of the globe. Their mission? To photograph a total solar eclipse that would either prove Einstein right or destroy his theory entirely. You see, Einstein had made an extraordinary prediction. Light from distant stars should bend as it passes near the sun. Not just a little bend, as Newton's physics might suggest, but precisely twice as much. The problem was, you could only test this during a total solar eclipse, when the sun's blinding light wouldn't overwhelm the starlight. On May 29, 1919, as darkness fell in the middle of the day, Eddington's teams, one in Brazil, another off the coast of Africa, photographed the stars visible near the sun's blocked face. When they compared these positions with photographs taken of the same stars at night, they found exactly what Einstein had predicted. The starlight had bent around the sun. The implications were staggering. Light, which travels in straight lines, was being curved by the sun's gravitational field, or more precisely, by the sun's warping of spacetime itself. Just as Einstein had claimed, massive objects weren't pulling on light with some mysterious force. They were bending the very fabric of space through which light travels. The announcement of these results made front-page headlines worldwide. Revolution in science, new theory of the universe, Newtonian ideas overthrown, proclaimed the Times of London. Almost overnight, Einstein became a global celebrity. A patent clerk from Switzerland had successfully challenged Newton's view of the universe that had stood for over 200 years. But this wasn't just about making Einstein famous. The light deflection experiment provided the first empirical evidence for something profound. Empty space isn't really empty. It's a dynamic, malleable fabric that can be bent and warped by the presence of mass and energy. Today, we see this light-bending effect everywhere we look in the cosmos. Massive galaxies act as gravitational lenses, bending and focusing light from more distant objects behind them. These cosmic magnifying glasses allow astronomers to see farther into the universe than ever before, revealing distant galaxies that would otherwise be invisible to us. We've even seen multiple images of the same quasar, its light taking different curved paths through space-time around massive objects, arriving at Earth at different times, a phenomenon known as gravitational lensing. Each of these observations confirms Einstein's prediction with increasing precision. The 1919 eclipse expedition didn't just verify a scientific theory. It fundamentally changed our understanding of the cosmos. It showed us that space itself has geometry, that light follows this geometry, and that the universe is far stranger and more magnificent than anyone had imagined. When Einstein first developed his theory of general relativity, he discovered something that deeply disturbed him. His equations suggested that the universe couldn't stand still. It had to be either expanding or contracting. This was so troubling to Einstein that he added a cosmological constant to his equations to force the universe to remain static. It would prove to be what he later called his greatest blunder. Enter Edwin Hubble, working at Mount Wilson Observatory in California. In 1929, using the world's most powerful telescope at the time, Hubble made an observation that would shake the foundations of cosmology. By measuring the light from distant galaxies, he discovered something extraordinary. The further away a galaxy was, the faster it appeared to be moving away from us. This was the first observational evidence of what we now call the expanding universe. The fabric of space itself is stretching, carrying galaxies along with it like raisins in an expanding loaf of bread. Einstein's original equations, before he added his cosmological constant, had predicted exactly this, a dynamic, evolving universe. The implications were staggering. If the universe is expanding, then winding the cosmic clock backward means everything was once closer together. Keep going back far enough, and you reach a moment when all matter and energy were compressed into an infinitely dense point, the Big Bang. General relativity had accidentally predicted the birth of our universe. But the story gets even more fascinating. In the 1990s, astronomers made another shocking discovery. The universe isn't just expanding, it's accelerating in its expansion. Something, which we now call dark energy, is pushing the cosmos apart faster and faster. Ironically, this mysterious force bears a striking resemblance to Einstein's discarded cosmological constant. This expanding universe helps explain many cosmic mysteries. It's why the night sky is dark despite the infinite number of stars, known as Olber's paradox. The expansion of space stretches light waves, making distant starlight redder and dimmer. It explains why the most distant galaxies we see appear different from nearby ones. We're seeing them as they were billions of years ago, when the universe was younger and different. Modern observations continue to refine our understanding of cosmic expansion. The Hubble Space Telescope, named after the astronomer who first discovered the expansion, has helped us measure the expansion rate with unprecedented precision. Yet mysteries remain. Different measurement methods give slightly different results, a puzzle known as the Hubble tension that might hint at new physics beyond Einstein's theory. The expanding universe also raises profound questions about our cosmic destiny. Will the expansion continue forever, leading to a big freeze where galaxies become so distant they can no longer see each other? Will dark energy tear apart the very fabric of space? Or is there some yet undiscovered mechanism that might reverse the expansion? Picture ripples spreading across a calm pond after you drop a stone. Now imagine these ripples occurring in the fabric of space and time itself. This is the essence of gravitational waves, one of Einstein's most remarkable predictions, and perhaps our greatest window into the most violent events in our cosmos. In 1916, Einstein's mathematics revealed something extraordinary. When massive objects accelerate, they should create ripples in space-time that spread outward at the speed of light. Like a cosmic game of telephone, these ripples carry information about the events that created them across the vast expanses of space. But these waves are incredibly subtle. Even massive cosmic events create ripples smaller than an atomic nucleus by the time they reach Earth. Einstein himself believed we would never be able to detect them. For nearly a century, these waves remained a theoretical prediction, dancing just beyond our grasp. Then, on September 14, 2015, everything changed. At precisely 5:51 a.m. Eastern Time, both detectors of the Laser Interferometer Gravitational Wave Observatory recorded a signal that would rewrite the history books. For a fraction of a second, they detected spacetime being stretched and squeezed by a passing gravitational wave. This signal, now known as GW150914, told an incredible story. Over a billion light-years away, two black holes, each about 30 times more massive than our Sun, had been spiraling toward each other. In their final moments, they merged at nearly half the speed of light, converting 3 solar masses of pure matter into gravitational wave energy. For a brief instant, this collision released more power than all the stars in the observable universe combined. Since that first detection, we've observed dozens more gravitational waves. We've seen black holes collide, neutron stars merge, and in the process, we've witnessed the birth of heavy elements like gold and platinum. Each detection opens a new chapter in our understanding of the cosmos. These waves are more than just ripples in spacetime. They're messengers from the most extreme events in our universe, carrying information that light itself cannot reveal. They let us see into the hearts of colliding black holes. They confirm Einstein's century-old predictions with extraordinary precision, and they've launched a new era of astronomy. Perhaps most excitingly, gravitational waves give us a whole new way to observe the universe. Traditional astronomy relies on electromagnetic radiation, light, radio waves, X-rays. But gravitational waves are fundamentally different. They pass through matter as if it weren't there, carrying pristine information about their sources across billions of light years. Today, a global network of gravitational wave detectors keeps constant watch on the cosmic ocean of spacetime. Each new detection helps us map the population of black holes in our universe, test Einstein's theory in new ways, and potentially discover entirely new types of cosmic events we never knew existed. The discovery of gravitational waves wasn't just a confirmation of Einstein's theory. It was the beginning of a new kind of astronomy. One that lets us listen to the symphony of the cosmos, hearing the ripples of spacetime itself as massive objects dance their cosmic ballet across the universe. These waves remind us that space isn't an empty stage where cosmic events play out. It's a dynamic, living fabric that stretches, bends, and ripples with the dance of massive objects. Every detection is a new verse in the cosmic song, telling us stories about our universe that we could never hear before. Imagine a place where the laws of nature, as we know them, break down completely. A cosmic abyss so deep that even light itself cannot escape. A region where time and space exchange roles, and the future points in only one direction, toward an infinitely dense center point. Welcome to one of the most extreme objects in our universe, the black hole. When Einstein published his theory of general relativity in 1915, he inadvertently predicted the existence of these cosmic monsters. At first, even Einstein himself was skeptical, but the mathematics was clear. If you pack enough mass into a small enough space, the curvature of spacetime becomes so extreme that it creates a point of no return, what we now call the event horizon. Think about that bowling ball on a bedsheet analogy we used earlier. Now imagine the ball being so heavy that it creates an infinite dip, a bottomless well in the fabric. That's essentially what a black hole does to spacetime itself. But the reality is even stranger than this simple analogy suggests. At the event horizon, spacetime becomes so warped that all possible paths lead to the center. It's not that light isn't fast enough to escape, it's that there literally is no path that leads away from the black hole. Every direction points toward the singularity at the center, where our current physics breaks down completely. Time itself behaves bizarrely near a black hole. From the perspective of someone falling in, time would appear to progress normally. But to an outside observer, time near the event horizon appears to slow down dramatically. If we could watch someone fall into a black hole, they would appear to slow down and freeze at the event horizon, their image growing fainter and redder until it finally fades away. We now know that black holes are not just mathematical curiosities. They're real, and they're everywhere. Supermassive black holes lurk at the centers of most galaxies, including our own Milky Way. Stellar mass black holes form when massive stars die in spectacular supernovae. Some black holes roam through space in binary systems, their gravitational dance producing the gravitational waves we've recently learned to detect. In 2019, humanity achieved something remarkable. We captured the first ever image of a black hole's shadow. The Event Horizon Telescope, a planet-wide network of radio telescopes, photographed the supermassive black hole at the center of galaxy M87. That image, a glowing ring of light around a dark center, provided visual confirmation of what Einstein's equations predicted a century ago. But black holes aren't just destroyers, they're also creators. Their immense gravitational fields can trigger star formation, their jets can seed galaxies with heavy elements, and their mergers send gravitational waves rippling across the cosmos. They play a crucial role in shaping the evolution of galaxies and the structure of our universe. Perhaps most intriguingly, black holes might hold the key to understanding quantum gravity, the holy grail of modern physics. At their centers, the infinite curvature of spacetime meets the quantum world in ways we still don't fully understand. They might even be gateways to other universes, though that remains in the realm of theoretical speculation. These cosmic objects, predicted by Einstein's theory over a century ago, continue to challenge our understanding of space, time, and the nature of reality itself. They remind us that the universe is not only stranger than we imagine, it's stranger than we can imagine. Every new observation brings new puzzles, new paradoxes, and new opportunities to push the boundaries of human knowledge into the darkest corners of the cosmos. You might think Einstein's theory lives only in the realm of cosmic phenomena and mathematical equations, but the truth is, you're using general relativity every time you navigate with your smartphone. Let's explore how this mind-bending theory affects our daily lives and shapes our understanding of the universe. Let's start with something you probably use every day: GPS. When you open your navigation app, you're relying on a system that wouldn't work without Einstein's insights. GPS satellites orbit about 20,000 kilometers above Earth, where time actually moves faster than on the ground, by about 45 microseconds per day. Add to this the effects of the satellite's high speed, which makes time move slightly slower, and you have a complex relativistic puzzle. Without accounting for these time differences, GPS would accumulate errors of about 11 kilometers per day. Your pizza delivery would never find your house, ships would drift off course, and aircraft navigation would be dangerously inaccurate. Every time you accurately arrive at your destination using GPS, you can thank Einstein's theory. But general relativity's applications go far beyond navigation. In the field of astrophysics, it's the foundation for understanding the most extreme phenomena in our universe. When astronomers study black holes, neutron stars, or gravitational lenses, they're using Einstein's equations. The recent image of the black hole at the center of M87? That was possible because general relativity told us exactly what to look for. In cosmology, general relativity is essential for understanding the very structure and evolution of our universe. The Big Bang Theory, the expansion of the universe, and the distribution of galaxies all emerge from Einstein's equations. When cosmologists try to understand dark energy, the mysterious force accelerating our universe's expansion, they're working within the framework of general relativity. The theory also plays a crucial role in particle physics. At the Large Hadron Collider, where scientists probe the fundamental building blocks of matter, relativistic effects must be considered. The very forces that hold atoms together can only be properly understood when we account for the curvature of spacetime. Modern technologies are increasingly relying on ultra-precise timing, where relativistic effects become important. Financial markets, where milliseconds can mean millions of dollars, must account for relativistic time differences between trading locations. Future quantum computers will need to consider relativistic effects in their calculations. In astronomy, general relativity helps us understand gravitational lensing, where massive objects bend light like cosmic magnifying glasses. Astronomers use this effect to study distant galaxies, search for exoplanets, and even map dark matter in the universe. The theory is also crucial for space exploration. When we send probes to other planets or plan future missions to distant stars, we must account for how gravity warps space and time. The famous slingshot effect, used to accelerate spacecraft, uses principles derived from general relativity. Perhaps most excitingly, general relativity is essential for developing new technologies. Gravitational wave detectors like LIGO are pushing the boundaries of precision measurement. Research into quantum gravity could lead to revolutionary new technologies we can barely imagine today. Even in medicine, general relativity has applications. Some medical imaging technologies must account for relativistic effects to achieve maximum precision. And who knows? Future medical devices might use gravitational principles in ways we haven't yet discovered. As we push further into the quantum realm and deeper into space, general relativity continues to guide our way. From the smartphones in our pockets to the telescopes peering into the cosmic abyss, Einstein's theory isn't just beautiful mathematics. It's a practical tool that helps us navigate both our daily lives and our greatest technological achievements. The most remarkable thing about general relativity might be this. Over a century after Einstein first proposed it, we're still finding new applications and implications. As technology advances and our understanding deepens, this elegant theory continues to reveal new ways to shape our future, both on Earth and among the stars. Despite its incredible success, general relativity still keeps physicists awake at night. Like a detective story with missing pieces, there are mysteries that Einstein's masterpiece hasn't fully solved. Let's dive into the most profound puzzles that continue to challenge our understanding of the universe. The biggest elephant in the room is what we call the quantum gravity problem. Imagine you have two brilliant friends who never agree with each other. That's essentially what happens when we try to reconcile general relativity with quantum mechanics. General relativity perfectly describes the cosmic ballet of planets, stars, and galaxies, while quantum mechanics explains the bizarre world of atoms and subatomic particles. Both theories work incredibly well in their own domains, but they simply don't play nice together. This disconnect becomes particularly problematic in extreme situations, like the center of black holes, or the first fraction of a second after the Big Bang. In these scenarios, both gravity and quantum effects are crucial, but our current theories give us mathematical nonsense when we try to combine them. This quest for a unified theory, often called the theory of everything, has consumed generations of physicists, including Einstein himself in his later years. Then there's the cosmic mystery of dark energy and dark matter. Observations tell us that ordinary matter, everything we can see, touch, or detect with our instruments, makes up only about 5% of the universe. About 27% is something we call dark matter, which we can only detect through its gravitational effects. The remaining 68% is even more mysterious. Dark energy, a seemingly anti-gravitational force that's causing our universe's expansion to accelerate. While general relativity can describe the effects of dark matter and dark energy, it doesn't tell us what they actually are. It's like having a perfect description of footprints in the sand without knowing what created them. Some physicists wonder if these mysteries might require modifications to Einstein's theory, while others believe the answers lie in better understanding the theory we already have. Perhaps the most perplexing puzzles emerge when we think about black holes. At their centers, general relativity predicts something called a singularity, a point where space and time themselves break down, and the mathematics of the theory stops making sense. These singularities are like mathematical warning signs, suggesting that our understanding is incomplete. The black hole information paradox adds another layer of mystery. Quantum mechanics tells us that information can't be destroyed, but black holes seem to break this rule. When objects fall into a black hole, what happens to their quantum information? Does it disappear forever? Is it somehow encoded in the black hole's radiation, as Stephen Hawking suggested? Or is there something fundamental we're missing about how space, time, and information are connected? We also face challenges in testing general relativity in extreme conditions. While we've confirmed the theory's predictions with remarkable precision in relatively weak gravitational fields, testing it near black holes, or in the earliest moments of the universe, remains incredibly challenging. New technologies like gravitational wave detectors are opening new windows, but many predictions remain just beyond our current experimental reach. Another fascinating question involves the very nature of time itself. General relativity treats time as a dimension, similar to space, but our experience of time flowing in one direction, what physicists call the arrow of time, isn't fully explained by the theory. Why do we remember the past but not the future? How does time's apparent flow emerge from timeless physical laws? These challenges aren't just academic puzzles, they point to deeper questions about the nature of reality itself. Is space fundamentally continuous, or is it discrete at the smallest scales? Do black holes really destroy information, or are we missing something fundamental about how the universe preserves quantum states? Could there be additional dimensions beyond the four we know about? Some theorists propose radical solutions, like string theory or loop quantum gravity, which attempt to resolve these issues by fundamentally reimagining the nature of space and time. Others suggest that we might need to embrace even stranger ideas, like the holographic principle, which suggests our three-dimensional reality might be a projection of processes occurring on a two-dimensional boundary. What's particularly exciting is that we're not just philosophizing. New experimental tools are helping us probe these questions. Gravitational wave observatories, ultra-precise atomic clocks, quantum computers, and powerful telescopes are pushing the boundaries of our understanding. Each new observation brings us closer to answering these fundamental questions, while often revealing new mysteries to explore. These challenges remind us that science is never truly finished. Einstein's theory revolutionized our understanding of the universe, but it also revealed new depths to our cosmic ignorance. As we continue to probe these mysteries, we're not just testing general relativity. We're pushing the boundaries of human knowledge and imagination, seeking to understand the deepest nature of reality itself. Few scientific theories have captured the public imagination quite like general relativity. Since its introduction in 1915, it hasn't just transformed physics. It has revolutionized how we think about our place in the cosmos and infiltrated popular culture in ways Einstein could never have imagined. Let's start with science fiction. The moment Einstein showed that time and space were flexible, writers and filmmakers began exploring the creative possibilities. From Interstellar to Doctor Who, from Star Trek to Contact, Einstein's ideas have provided the scientific foundation for countless stories. Wormholes, time travel, faster-than-light travel. These staples of science fiction all trace their origins to general relativity's mathematical predictions. When Christopher Nolan created the film Interstellar, he actually hired physicist Kip Thorne as a consultant to ensure the depiction of the black hole Gargantua was scientifically accurate. The resulting visual effects were so precise that they led to scientific publications about black hole visualization. This shows how art and science can feed into each other, creating a beautiful cycle of inspiration and discovery. The theory has also profoundly influenced philosophy. When Einstein showed that time itself was relative, that simultaneity depends on the observer, and that gravity is the curvature of spacetime, he wasn't just changing physics, he was challenging fundamental assumptions about the nature of reality. Philosophers had to grapple with questions like, if time isn't absolute, what does that mean for free will? If space and time are intertwined, what does that tell us about the nature of existence? The philosophical implications extend to our place in the cosmos. General relativity led to the Big Bang theory, suggesting that our universe had a beginning and might have an end. This scientific origin story has influenced religious and philosophical discussions about creation and purpose, showing how a physical theory can shape our deepest existential questions. Then there's Einstein himself. The wild-haired physicist has become the ultimate symbol of genius in popular culture. His name is synonymous with brilliance. We call exceptional people Einsteins, and his famous equation E equals mc squared appears on everything from t-shirts to tattoos. He's become a shorthand for revolutionary thinking, for seeing beyond conventional wisdom to deeper truths. This iconography has had a lasting impact on how we view scientists and scientific discovery. Einstein showed that the most profound insights could come from pure thought and mathematical beauty, rather than just experimental observation. His famous thought experiments, imaging riding alongside a beam of light or being in a falling elevator, showed how imagination and creativity are essential to scientific progress. The theory has also influenced art and literature beyond science fiction. Salvador Dali's melting clocks in The Persistence of Memory are often interpreted as a reference to Einstein's flexible time. Writers like Thomas Pynchon have incorporated relativistic concepts into their work, using them as metaphors for human experience and perception. In modern popular culture, general relativity continues to inspire. Black holes have become powerful metaphors for inescapable attraction or points of no return. The concept of warped spacetime appears in video games, music lyrics, and visual art. Every time a movie shows a spacecraft using a gravitational slingshot maneuver, it's paying tribute to Einstein's insights. The theory has even influenced how we think about truth and perspective in broader contexts. The idea that different observers might see events differently, yet both be correct within their frame of reference, has become a powerful metaphor for understanding cultural and personal differences. Social media and the internet age have given Einstein's ideas new life. Memes about relativity, time dilation, and black holes spread across the web, making complex physics concepts part of everyday conversation. YouTube channels and science communicators use creative animations and explanations to make these ideas accessible to millions. Perhaps most importantly, general relativity has shaped our collective imagination about what's possible. It showed us that the universe is far stranger and more wonderful than common sense suggests. When we look up at the stars today, we don't just see points of light. We see warped space-time, gravitational lenses, and the cosmic dance of curved space. The theory reminds us that the most fundamental aspects of our reality, space, time, gravity, are more mysterious and malleable than we imagined. This has encouraged us to question other assumptions, to look deeper, to imagine bigger. In showing us how strange the universe really is, Einstein's theory didn't just change physics. it changed how we dream about what's possible. As we face new challenges in the 21st century, from quantum computers to space exploration, general relativity continues to inspire new generations. It stands as a testament to the power of human imagination and mathematical beauty to reveal profound truths about our universe. More than a century after its introduction, it remains not just a scientific theory, but a cultural touchstone that reminds us how far human understanding can reach. Imagine being able to unravel the deepest mysteries of the universe simply by using your mind. That's exactly what Einstein did with his brilliant thought experiments. Let's explore two of his most famous mental exercises that revolutionized our understanding of space, time, and gravity. First, let's step into Einstein's elevator, perhaps the most elegant thought experiment in the history of physics. Picture yourself in an elevator, but not just any elevator. This one is floating somewhere in deep space, far from any gravitational influence. Now, imagine this elevator is being pulled upward with a constant acceleration equal to Earth's gravity. Here's the brilliant insight. Standing inside this accelerating elevator, you would feel a force pushing you down, exactly like gravity on Earth. Drop a pen, and it would fall to the floor. Jump, and you'd come back down. Every experiment you could perform would be identical to what you'd experience in a stationary elevator on Earth. Einstein realized something profound. There is no experiment you could conduct inside the elevator to determine whether you're in a gravitational field or accelerating through space. This is what we call the equivalence principle, the cornerstone of general relativity. Gravity and acceleration are two sides of the same coin. Take this idea further. If the elevator were in free fall toward Earth, you would feel weightless, exactly the same sensation astronauts experience in orbit. Einstein realized that gravity isn't really a force at all. It's the curvature of spacetime itself. When we feel gravity, we're actually feeling the geometry of curved spacetime. Now, let's meet the traveling twins, Alice and Bob. This thought experiment explores one of relativity's most mind-bending predictions, time dilation. Alice stays on Earth while her twin brother Bob boards a spacecraft traveling at nearly the speed of light to a distant star. From Bob's perspective on the spacecraft, his journey might last only a few years. But when he returns to Earth, he finds that Alice has aged much more. Perhaps decades have passed for her. This isn't science fiction. It's a real prediction of relativity, confirmed by precise atomic clocks. Time really does run slower for objects moving at high speeds relative to us. The twin paradox reveals something fundamental about time. It's not universal. The time you experience depends on your path through space-time. Every time you move, you're actually taking a different path through time than someone standing still. The effect is tiny at everyday speeds, but becomes dramatic as you approach the speed of light. What makes these thought experiments so powerful is their simplicity. Einstein didn't need expensive equipment or complex mathematics to develop these ideas. He used pure reasoning and imagination to reveal fundamental truths about our universe. The elevator experiment shows us that what we call gravity is indistinguishable from acceleration. This simple insight led Einstein to realize that gravity isn't a force reaching across space. It's the result of massive objects curving the fabric of spacetime itself. When planets orbit the Sun, they're actually following the straightest possible paths through curved spacetime. The twin paradox, meanwhile, demonstrates that time itself is flexible. There's no universal clock ticking away in the background of the universe. Time flows differently for different observers, depending on their relative motion and the gravitational fields they experience. These thought experiments weren't just philosophical exercises. They led to testable predictions. GPS satellites must be programmed to account for both the time dilation from their speed and the gravitational effects from their altitude. Without these corrections, the entire system would fail within minutes. The beauty of these thought experiments lies in their accessibility. You don't need a PhD in physics to understand the basic principles. Einstein showed us that the deepest truths about our universe can be approached through careful reasoning and imagination. They also reveal Einstein's unique genius, his ability to see beyond the mathematical formalism to the physical reality beneath. Where others saw complex equations, he saw elevators and twins, turning abstract physics into tangible scenarios that anyone could understand. Today, these thought experiments continue to help students and scientists understand the principles of relativity. They remind us that sometimes the most powerful scientific tools aren't particle accelerators or space telescopes, but the human mind's ability to imagine and reason about the nature of reality. In an age of increasingly complex technology and specialized knowledge, Einstein's thought experiments stand as a testament to the power of simple, clear thinking. They show us that the greatest scientific insights often come not from complicated machinery, but from asking the right questions and following them to their logical conclusions. These mental exercises changed our understanding of space, time, and gravity forever. They remind us that the universe is stranger and more wonderful than our everyday experience suggests, and that sometimes the best laboratory is the one between our ears. When Albert Einstein passed away in 1955, he left behind much more than a collection of equations and theories. His legacy continues to shape our understanding of the universe, influence technological development, and inspire new generations of scientists. Let's explore the profound and lasting impact of Einstein's work. Einstein's work fundamentally transformed how we think about the universe. Before relativity, physics was built on Newton's concepts of absolute space and time. Einstein showed us that reality is far more subtle and interconnected. Space and time aren't separate, unchanging backdrops, but are dynamically linked and influenced by matter and energy. His famous equation E equals mc squared didn't just give us a mathematical relationship, it completely changed our understanding of matter and energy. This single equation explained why stars shine, led to nuclear power, and showed us that the universe is far more dynamic than we imagined. The mathematical framework Einstein developed for general relativity introduced entirely new ways of thinking about physics. The idea that gravity isn't a force but a consequence of curved spacetime opened up new mathematical approaches that influence physics to this day. Modern theories in physics, from string theory to quantum gravity, build upon Einstein's geometric approach to understanding the universe. It's no exaggeration to say that many modern technologies wouldn't exist without Einstein's insights. GPS satellites require relativistic corrections to function accurately. Nuclear power plants operate on principles derived from his work on mass-energy equivalence. Modern astronomical observations, from gravitational lensing to black hole detection, rely on his theories. Einstein's work also laid the groundwork for numerous technological developments: laser technology, which builds on his work on stimulated emission; solar cells, which exploit the photoelectric effect he explained; nuclear magnetic resonance, leading to MRI machines in hospitals; precise atomic clocks, essential for global navigation and communication; gravitational wave detectors, opening a new window on the universe. His theories continue to guide space exploration, satellite technology, and our understanding of cosmic phenomena. When scientists announced the first image of a black hole in 2019, they were confirming predictions Einstein made over a century ago. Perhaps Einstein's most powerful legacy is how he continues to inspire scientists and thinkers. His approach to physics, using thought experiments, visualizations, and mathematical beauty to uncover physical truth, showed that creativity and imagination are essential to scientific progress. Einstein demonstrated that questioning established wisdom and thinking differently can lead to revolutionary insights. His famous quote, "Imagination is more important than knowledge," encourages scientists to look beyond existing frameworks and dare to propose radical new ideas. His work ethic and persistence are equally inspiring. It took Einstein 10 years of intense work to develop general relativity, showing that great scientific achievements often require sustained dedication and effort. Yet he maintained his curiosity and sense of wonder throughout his life, reminding us that the best scientists never lose their capacity for amazement at the universe's mysteries. Einstein's influence extends far beyond physics. His ideas about the nature of reality, time, and causality have influenced philosophy, art, and literature. His famous debates with Niels Bohr about quantum mechanics raised deep questions about the nature of reality and measurement that we're still grappling with today. He also set an example as a public intellectual who spoke out on social and political issues. Einstein used his fame to advocate for peace, civil rights, and international cooperation, showing that scientists can and should engage with broader societal issues. Even today, Einstein's work remains at the forefront of physics. The search for a quantum theory of gravity aims to reconcile his theories with quantum mechanics. Dark energy and dark matter investigations build on his cosmological framework. Quantum entanglement, which he famously called spooky action at a distance, is now central to quantum computing research. New tests of general relativity continue to confirm and refine his predictions. Einstein also left us with important, unresolved questions that continue to drive physics forward. How can we reconcile general relativity with quantum mechanics? What is the nature of dark energy and dark matter? How do we resolve the black hole information paradox? Is there a more fundamental theory underlying relativity? As we move into an era of quantum computers, space tourism, and possibly interplanetary travel, Einstein's theories become even more relevant. His work will be crucial for navigation in deep space, understanding quantum gravity, developing new energy technologies, managing time synchronization in global networks, future cosmological discoveries. Einstein's legacy reminds us that fundamental research, even when it seems purely theoretical, can lead to profound practical applications. His work continues to be both a foundation for practical technology and a source of deep questions about the nature of reality. Perhaps most importantly, Einstein showed us that the universe is both more mysterious and more comprehensible than we imagined. His legacy encourages us to keep questioning, keep wondering, and keep searching for deeper understanding. In this way, every new discovery in physics carries forward Einstein's legacy of curiosity, creativity, and courage in pursuing radical new ideas. As we face new challenges in physics and technology, Einstein's example reminds us that the most important discoveries might come from asking simple questions and following them to their profound conclusions. His legacy isn't just about what he discovered, it's about how he approached the mysteries of the universe with creativity, persistence, and wonder. Einstein's general theory of relativity stands as one of humanity's greatest intellectual achievements, not merely a mathematical description of gravity, but a fundamental reimagining of the very nature of reality itself. Over a century after its inception, this elegant theory continues to unveil new secrets about our universe, proving itself to be both profound and practical in ways Einstein himself could never have imagined. The theory's enduring power lies in its ability to explain everything from the daily operation of GPS satellites to the cosmic dance of colliding black holes. It has predicted phenomena that seemed like science fiction at the time: black holes, gravitational waves, the expansion of the universe, only to have each prediction validated by increasingly sophisticated observations. But perhaps the theory's greatest impact has been philosophical. General relativity forever changed our understanding of space, time, and gravity. It revealed a universe where space and time are not fixed backdrops but dynamic, interrelated aspects of a single cosmic fabric. Gravity emerges from the geometry of spacetime itself, not as a mysterious force acting at a distance. The universe is not static but breathing and evolving, with a beginning and potentially an end. Time flows differently depending on where you are and how you're moving. The very large and the very small are connected in ways we're still trying to understand. Looking forward, general relativity continues to drive scientific exploration and technological innovation. From the detection of gravitational waves opening a new window into the cosmos, to the ongoing quest to reconcile quantum mechanics with gravity, Einstein's theory remains at the frontier of physics. Yet, like all scientific theories, general relativity has its limits. It breaks down at the singularity of a black hole and struggles to explain quantum phenomena. These limitations don't diminish its achievement. Rather, they point the way toward even deeper theories that might one day supersede it, just as general relativity built upon and transcended Newton's work. As we face the mysteries of dark energy, the nature of black holes, and the earliest moments of the Big Bang, general relativity remains our most reliable guide to understanding the large-scale structure of the universe. It reminds us that reality is far more magnificent and mysterious than our everyday experience suggests, and that the pursuit of understanding can reveal truths more amazing than anything we could have imagined. In Einstein's curved universe, we find not just a description of gravity, but a testament to human ingenuity and imagination. Proof that with mathematics, reason, and creativity, we can unlock the deepest secrets of the cosmos. As we continue to explore and understand our universe, general relativity stands as both foundation and inspiration, reminding us that the greatest discoveries may yet lie ahead.